Hello, everyone, and thank you for joining us today. Welcome to Mega's special webinar series. Today's topic is Cable Condition Assessment, VLF, and 10 Delta Testing. My name is Michael Fleischer, and I'm the Digital Marketing Specialist for Mega. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions during the Q&A segment at the end of the webinar. Additionally, the certificate of attendance, copy of the presentation, and link to the recording of this webinar will be sent to all attendees in about 2 business days. Our presenter today is Javier Ruiz, Applications Engineer. Also, to assist with the question and answer session, we will have joining us Henning Oetjen, Product Manager, and Robert Probst, Product Manager. All right, let's go ahead and get started. Thank you for joining us today, Javier.
Thanks, Michael, and thank you all for attending this webinar. Let's start by doing a quick review of the agenda for this webinar. We'll start talking of the medium voltage cables, the medium voltage cable construction, the failure mechanisms in medium voltage cables, the local problems, the global problems, and the medium voltage cable life. We'll continue talking about cable maintenance, VLF tests. What is the VLF test, the parameters, goals, and standards. We'll continue talking about the 10 delta test. What is the 10 delta test? We will use a theoretical approach to show how the 10 delta test works. We'll continue talking of the parameters, the assessment criteria, and how to interpret the results. And we'll finish this webinar doing a simulation of a VLF test and a 10 delta test using the VLF sinus 45 kV of Mega. So let's start talking of the cable construction in medium voltage cables. The picture that we are seeing in this slide is the classical construction of a single phase medium voltage cable, in which we have a center conductor that could be of copper or aluminum material. Then we have the inner semicon or the semicon layer over the conductor. Next, we have the main insulation. In this case, is XLPE insulation. The next one that we have is the outer semicon layer, or the semicon layer over the insulation. And then we have the shield or the neutral concentric of the cable. And finally, we will have the jacket or the sheath of the cable. The typical voltages for medium voltage cables are 15, 25, and 35 kV. So continue talking of the cable construction of medium voltage cables. We could have, besides the single phase shielded medium voltage cable we saw in the previous slide, we can have also the 3-core cable, in which we have 3 conductors and each one has its individual shield. In the picture at the bottom of the slide, we are seeing a delta cable. In this case, we have also 3 conductors, but with 1 common shield. So this is some of the different constructions we can have in medium voltage cables. Regarding the insulation for medium voltage cables, we have mainly 2 types of insulations. What we can call solid dielectrics or plastic cables, or also polymeric insulations. The EPR and the XLPE are the most common solid dielectrics insulations in medium voltage cables. And the other type of insulation we have is the paper insulated cables, or also laminated dielectrics. In terms of the tests that we do for this kind of insulations, we have the IEEE 400.2 for the VLF test in solid dielectrics, or in insulations as could be the EPR and the XLPE. And for the paper insulated cables, we have the IEEE 400.1. Okay, we can use also the VLF to test paper insulated cables, but of course it's very well known that we cannot use any longer the high pot DC in EPR or XLP insulations. For the 10 delta, And for the partial discharge, we can use also the VLF in EPR, XLP, and paper insulated cables. And for partial discharge, we have additional the IEEE 400.3, and for the damped AC wave shape, we have the IEEE 400.4. That will be all the standards that apply for VLF, 10 delta, and partial discharge tests in medium voltage cables. Talking of the failures mechanisms in medium voltage cables, we should distinguish between the local issues or the local problems and the global problems. A local issue, it's a problem that is limited to one portion, one segment of my cable. It's not a problem that is spread along all the cable. It's just a problem that is constrained to a segment or accessory in my cable. For instance, if I have a problem in a termination, I will consider that a local problem because it's just the termination that has a fault, and if I replace the termination, the cable will recover all at 100% its operativity. Or if I have, for instance, a fault or a weak spot in the insulation of my cable because maybe somebody bend too much the cable and I have a small bending radius in my cable, well, when that happens, sometimes we inflict a mechanical damage in the insulation of the cable, or it could be that if we bend too much the cable between the layers of the cable, maybe it's between the semicon layer over the insulation, we will have air bubble. And when the cable will be in service, we will have starting a PT activity in that air bubble, and sooner or later we will have a fault. So if you see, the local issues are in one portion of the insulation or affect specific one splice or a termination. By the other hand, we have the global issues, and the global issues will be spread along all the cable. In the case of XLPE cables, we have the wire trees. The wire trees are insulation aging condition in the XLPE cables, in the polymeric cables. And in the case of the paper insulated cables, we have the cellulose degradation. So depending on what problem I'm dealing with is the tool or the diagnostic or test I will use. For instance, if I am dealing with severe installation and or manufacture issues, I can use the VLF. The VLF will convert in fault all the severe installation and or manufacture problems. But if I am looking for incipient installation or manufacture problems, then I need to use the partial discharge diagnostic. And if by the other hand, I am looking for age insulation issues in my cable, in the insulation of my cable, if I'm looking, for instance, for wire trees, I can use the 10 delta. So depending on what I'm dealing with what problem I am dealing with, is the different tests I can use. Regarding local problems, some examples of local problems in the first two pictures, we can see high voltage splice that was bad assembled, or in the other picture we see a medium voltage joint. In this case, it's a heat shrink joint splice, and the guy that did this splice didn't heat uniformly the splice. So they leave a little air bubble inside of the splice. And when the cable was in service, we started with the partial discharge activity in this air bubble. And this is the classic local issues example, or local issues, a bad workmanship that can affect, in this case, the manufacturer of the splice. The next two pictures are examples of also bad workmanship issue In this case, the guy that fixed the cable in the holders exceed the torque, and when they exceed the torque, they deformed the cables, and that inflicted a mechanical damage in the insulation of my cable. And the last two pictures are the classical termination problems, maybe because the guy that did the termination didn't respect the lengths of the termination, or maybe because during the elaboration of the termination there was some contamination in the termination. So all these are classical examples of local problems, and they are related mainly with a bad workmanship or manufacturer defects. By the other hand, we have the global problems. And if we will talk of global problems, we should keep in mind that all the medium voltage power cables have a high life expectancy. But during the whole service life, they will be subject to thermal, electrical, mechanical, and environmental stresses. And these stresses will change the morphological properties of the insulation. In other words, these stresses will age and degrade the insulation material of my cable, and the result is a decrease of the breakdown strength of the insulation, and the decrease of the insulation breakdown strength will finally lead to a cable failures. So continue with the aging mechanism. In the case of XLP cables, of course, we have the wire trees. The wire tree is a chemical degradation of the insulation, and all start with the ingress of water in the insulation of my cable by diffusion, or maybe because we have sheath faults. So the ingress of water together with the electrical stress in my cable will start the generation and growth of wire trees. And this will be a very, very long process that will take at least 5 years. But once the wire tree reaches its critical size, like is in this point, the wire tree will convert in an electrical tree. And an electrical tree is a progressive carbonization of the insulation. What happens is that every time this wire tree is growing up, we will have a higher field stress in the other side of the insulation. And there is the no-return point when we have the starting of the partial discharge and then the electrical tree. And finally, we will have a fault. So this is pretty much the process from when starting with the wire tree and then the conversion in an electrical tree. So in the case of XLP cables, we have, of course, the wire trees are the most important aging phenomenon for polymer cables and could lead into early cable faults, as we saw in the previous slide. In the case of paper insulated cables, of course, the most important aging phenomenon for paper insulated cables is the degradation of the cellulose. What basically means is that the moisture comes free from the paper insulation because of thermal and chemical process, and of course the corrosion of the other sheath and the generation of holes in the lead sheath will originate an increase of moisture content. What happens is that the external water will ingress in the cable if we have corrosion on the other sheath or holes. So we could say that the medium voltage lifetime, of a cable is pretty much like a bad tooth, in which at the beginning we will have teething troubles. Then we will have some period of time in which we will have no too much faults, maybe some unexpected breakdowns due to operation conditions, and in the last third of the lifetime of a cable will start with aging breakdowns. So now we know this, we can the line, the strategy for the maintenance in my cable. And of course, the goal is the increase in the reliability of the system. And we can use preventive maintenance, as could be the VLF test, or predictive maintenance, as could be the 10 delta and the partial discharge, depending what I'm looking for. And of course, the goal is the reduction in the outage minutes. And we would like to have we would like to keep the SAIFI and the SAIDI indexes very low, and we need to have an asset management. We need to have an optimal allocation of the limited resources and technical and systematic approach for the invest. In other way, what we want to have, we need to have is a cable replacement program. Once we know that, we can, as I said, line the strategy to increase the cable reliability, and all will start with the commissioning test of newly installed cable circuit, and will end with the replacement of the entire cable or sections of it. But in between, we should we need to have the periodic maintenance testing of service aged cable circuits. So we can use for the commissioning test the VLF test on the partial discharge diagnostics, and for the periodic maintenance, we can use the VLF, the 10 delta, and the partial discharge test. So let's start talking of VLF. What is VLF? Well, fundamentally is an AC over voltage test. Also, we call it AC hypot. We will use the frequency at 0.1 hertz. So VLF, during the VLF, we will apply an AC over voltage with a frequency of 0.1 hertz. And it's pretty much like a pressure test. We will apply a voltage above operating, and these voltages will be prescribed by IEEE 400.2. And what we are doing is looking for breakdowns. What we want to do during a VLF test is convert in faults the big problems in the installation or the accessories of my cable. So the VLF test is a pass-fail test, and we will have limited diagnostic information. If we are looking for more specific information of the condition of the insulation of my cable, or the condition of the termination and splices, we need to use the PD test or the 10 delta test. The VLF will not give us that information. So talking of the VLF parameters, we have, of course, the voltage, the wave shapes, the voltage, the time, and the frequency. In terms of the wave shapes, we have two technologies, the sinus wave shape and the cosinus rectangular wave shape. Regarding the voltage, the test voltage levels are between 2 times U0 and 3 times U0, where U0 is the rated RMS phase to ground voltage. And the test time is between 30 and 60 minutes, and as I said, the frequency must be 0.1 hertz. Regarding of the pros and cons of the two technologies, the sinus technology and the cosinus rectangular technology, we can see in this slide that, for instance, for the VLF sinus at 0.1 hertz, the pros are that we have a lighter, smaller, and cheaper units than the cosinus rectangular units. Also, with one advantage of the VLF sinus at 0.1 hertz is that we can perform the 10 delta test. The cons of the VLF sinus at 0.1 hertz is that we apply a peak voltage. The liquid current measurement is not possible, and we have a small test capacitance at 0.1 hertz. So we will not be able to test long cables at 0.1 hertz. Only by decreasing the frequency is that we can test longer cables with the VLF sinus wave shape. But if we decrease the frequency when we are doing a VLF sinus test, we need to keep in mind that the rod rate of the electrical threads will change. Let's see this graphic. In the horizontal axis, we have the test voltage. In the vertical axis, we have the rod rate in millimeters per hour of the electrical threads. So the red graph shows me the growth rate versus the test voltage for the sinus wave shape at the frequency 0.1 hertz, 0.1 hertz. And you can see that the growth rate of the sinus wave shape at 0.1 hertz, it's 10 millimeters per hour. In the case of the cosinus rectangular wave shape at the same frequency, 0.1 hertz, we have pretty much the same growth rate for the electrical threads, 10 millimeters per hour. But if we decrease the frequency in the sinus wave shape, if we decrease the frequency, for instance, at 0.01 hertz, the growth rate will decrease 10 times. You can see here in the purple or pink graph that if we apply the same voltage, 3 times the test voltage, the growth rate will decrease at 1, which means that if we decrease the frequency, we decrease the growth rate of the electrical threads, and that means that we'll need increase by 10 the test time of my test. So you need to keep that in mind when you decrease the frequency, when you are doing a VLF test with a sinus wave shape. If you decrease the frequency, you need to increase the time in the same proportion, okay? So continue with the cons of the VLF sinus. We have, of course, that the PD test results are not comparable with the power frequency results. There is a frequency dependence of the partial discharge, which means is that when you do a partial discharge test at power frequency, you will see some PD activity that if you decrease the frequency at 0.1 hertz, you will not see. So the partial discharge has a dependency of the frequency, and if you reduce the frequency, you go below the 60 hertz, some partial activity will disappear. Continue with the VLF cosine rectangular pros. We have a higher test capacitance. The change of polarity matches with the power frequency. I will explain this in the next slide. We can measure the leakage current. We apply a RMS voltage, and we can use the damped AC wave shape for partial discharge. This is some advantage that we have with the cosinus rectangular wave shape. And there is a specific standard, the IEEE 400.4, that discusses and talks about of the partial discharge test using the damped AC. The cons of the VLF cosinus rectangular is that we cannot measure the tan delta, and normally the units are more expensive than the sinus, bigger and heavier. So this is some of the cons that we have with the cosinus rectangular wave shape. To explain what I mentioned, that the cosinus rectangular wave shape change of polarity matches with the power frequency, we have the next slide. If you see, what we have here is the 3 wave shapes I mentioned in the last slide. We have this in orange, we have the VLF sign. Then we have in black the cosinus rectangular wave shape, and in red we have the damped AC. And in power, and the power frequency is all this blue color. Okay, so we will go through.
Javier, it seems like we've lost your audio.
The
Could you try and
different
readjust?
cycles, we start to see the behavior of the. Hello, can you hear me?
Yeah, we're good. We got that fixed. Continue.
Michael?
You're all set. Yep.
Okay.
Yeah, your
Yeah,
audio
thank
came
you.
back real.
So I was talking that in this slide we have, you can hear me, okay? Hello? Yeah, I can
Yep, we're
continue,
all set.
Michael.
We're good. Yes, continue.
Okay, thank you, sorry. So in this slide, what we are seeing is the three wave shapes I mentioned in the previous slide. I have the orange one is the VLF sinus, the black one is the cosinus rectangular wave shape, and the red one is the damped AC. So, and the blue one is the power frequency. So when we go through the different cycles, you can see what I mentioned, that the change of polarity of the power frequency. And in the case of the damped AC, the behavior of the damped AC is pretty much the same that the power frequency, but is not the case of the VLF sinus wave shape. So this is something that is important to keep in mind especially when we talk of how we excite the electrical threes. The way we excite the electrical threes will be pretty much the same when we use the cosine rectangular wave shape or when we use the damped AC for partial discharge, but not the same when we use a VLF sinus wave shape. So now talking of the test voltages prescribed by the IEEE 400.2, depending of what kind of technology we are using, if we're using a sinusoidal wave shape or a cosinus rectangular wave shape, we will have the different voltages in the IEEE 400.2. Just to show you the difference between the voltages for the two technologies, we have for the same rated cable, 15 kV, that for acceptance test, doing a sinus VLF test, we'll apply 21 kV RMS, which means 30 kV peak. In the case of the cosine rectangular, the RMS and the peak voltage are the same. For this reason, we have 30 kV. So the goals of the VLF test are improve the reliability of the system, accelerate the existing weak spot to failure, of course, during a scheduled outage, under controlled test conditions, and at reduced energy levels. This last is very important. At reduced energy levels is not the same that I have a fault when the cable is in service, that I have a fault when I'm doing a VLF test. And the big difference is the amount of energy that will be liberated through the fault. Of course, when the cable fails during service, I will have a higher amount of energy, and for that reason, I will have I could have collateral damage. When the cable fails during a VLF test, the energy, of course, is smaller, and for that reason, I have a limit collateral damage. And the other goal is that we will repair and replace on planned and proactive basis, not on planned and reactive way. The applicable standards for the VLF are the IEEE 400.2, that is for mainly, I will say, for USA, Canada, and Mexico. We have also the VDE, that is the German standard. We have the Senelec, that is the European standard, and we have also the IEC, that is the international standard. So doing a brief summary of the VLF test, we can say that 0.1 Hertz VLF testing is the state of the art of cable test method. It's effective to be used by construction crews as a substitute for the DC hypo test before switching circuit in. Is effective as with stand test to detect low and high resistive local defects in cable systems. Of course, provided that the proper test parameters are being used. That is something that happens very often. The people is afraid to apply high voltage in the cables or do the VLF test during the time of maybe 30 minutes or 60 minutes. And if we decrease the voltage or will decrease the test time, we are not doing an authentic and true VLF. We are doing a fake VLF test. So we need to use always the voltages and the test times recommended by the standards. But what the VLF doesn't tell you is the overall condition of the cable. So if you are looking for high losses or wire trees, or to know how good or bad is the cable insulation, you will not be able to get that information doing a VLF test. Then you need to, if you are looking for that specific information, you need to use the tan delta test. And I will start to talk of the tan delta test in the next slide. So, what is the tan delta test? Well, the tan delta test is a global method of testing cables to determine the remaining life expectancy of the insulation. We know that there is a correlation between an increasing of 0.1 hertz tan delta and a decreasing insulation breakdown voltage level at power frequency. Then we know that that correlation exists. Indeed, this is an extract of the IEEE 400.2, and the tan delta test is based on VLF technology. Of course, it's a diagnostic test and it's a prescribed test method by the IEEE 400.2. When to use the tan delta? Well, typically we will use the tan delta on aged cables that have been in service at least 5 years. The goal is to detect the aging conditions in the insulation of the cables, and we can use the tan delta test as part of a cable maintenance strategy to alert critical aged cables to before in-service faults and up to 1 to 2 years notice. And for instance, what the goal is that if we have all these old cables in the pictures and we want to start to replace the cables with the worst aging conditions in the insulation, then we can use the tan delta as part of cable replacement project, and the tan delta will help us to target the worst cables first, not the older ones. Not necessarily an older cable is a bad one or a aging cable. It could be that maybe a cable that is less old than other one has worse aging conditions in the insulation. So the idea of the tan delta is to help us to target the worst cables first and to use wisely the available money. So why to use the tan delta? Because it's a non-destructive test. We will see in the coming slides that the maximum voltage I will apply during the tan delta test is 1.5 GNOT. So it's very unlikely to fault the cable during or after a tan delta test. It's a diagnostic tool to estimate the remaining life of the cable. And of course, the goal is to detect the aging conditions in the insulation of my cable. And of course, what we want to do is to increase the system reliability of the cable system. What we can detect with the tan delta? Well, the tan delta will provide an overall condition assessment, and we will estimate the life left in the cable. We can detect wire trees in XLP cables, contaminants in the insulation, insulate moisture, degraded accessories, for instance, the terminations, and oil leakage in paper insulated cables. And also we can assess effectiveness of repairs before and after the measurements. So this is what we can detect with the tan delta. What we cannot detect is we cannot locate discrete problems. Only that there is or is not a problem, but we cannot know about what problem is. What specifically the problem is. It's a corroded concentric or it's a wire trees. And also we will not be able to detect with the tan delta problems in the jacket or lead shield. We will not detect also poor workmanship or manufacturer defects. So how the tan delta works? I will use a very simplistic way to show you how the tan delta works. Let's consider for this example that this circuit represents a cable with a perfect insulation. Okay, so this circuit represents a cable with a perfect insulation. If that is the case, that we have a cable with a perfect insulation, then the value of the resistance of this resistor will be very high, will trend to infinite. Okay, if the value of the resistance in this resistor trends to infinite, that means that the resistive current will not be able to go through this resistor, and all the current circulating in this circuit, all the current circulating in my cable with a perfect insulation will be the capacitive current going through this capacitor. Okay, and if I need to graph the voltage and the current for this specific situation, I will have something like this, in which I have the voltage shifted a 90 degrees angle of the capacitive current, and keep in mind that the resistive current it's equal to 0. Now let's consider that the insulation in my cable is no longer perfect. So we start to see some current going through this resistor. So the value of the resistance no longer trends to infinite. Is no longer a perfect insulation, is no longer a perfect resistor, and we will start to see going through this resistor some resistive current. So this graph no longer represents what is happening in my circuit, and what really represent what is happening right now is this one, in which I have the voltage and I have a vector that represents the total current in my circuit, and this vector of the current has two components: the resistive current, that is this is small one vector, and this one that is the capacitive current. So the delta angle is a good indicator of how good or how bad is the insulation of my cable. If this delta angle trends to 90 degrees, means that the resistive current is growing up in my cable, so that means that I'm losing insulation. If by the other hand this delta angle trends to 0, I have the situation in the graph in the left, in which the resistive current is equal to 0, which means that I have almost a perfect insulation. So this is the delta angle, and the trigonometric function that correlates the resistive current and the capacitive one is the tan delta. So the tan delta is the trigonometric function that correlates the resistive current and the capacitive one. So which means that if I have a very high tan delta, I need to have a very high resistive current, which means that I am losing insulation. If by the other hand, I have a really low value of the tan delta, that means that my resistive current is really small. So that means that I have almost a new insulation. This is pretty much what is the way how the tan delta works. So what we need to have to do a tan delta test? Well, we have to have a US. We need to have a sine wave shape, a sinus wave shape. The frequency that we will use is 0.1 hertz. 0.1 hertz must be the frequency, and in each voltage step we will measure between 8 to 10 times the tan delta values. So we will apply 3 voltage steps. The first one will be 0.5 U naught. The second one will be 1.0 U naught, and the last one, the third one will be 1.5 U naught. So why we need to use a sinus wave shape to do the tan delta? Well, the reason for that is that, for instance, in a purely capacitive circuit, the current leads the voltage by a 90 degree angle, and remember that we need to have the reference of the shift angle between the voltage and the current, as we saw in the previous slides. So we need that reference. In a cosine rectangular wave shape, we lost that reference. We don't have the phase reference between the current and the voltage. Okay, for that reason, we need a sinus wave shape to do the tan delta test. But also, what we have with the cosine rectangular wave shape, as we see these plateaus in the cosine rectangular, is that we can measure the liquid current, because in this plateau we have a stabilization of the voltage, which allow us to measure only the liquid current, what we cannot do with a sinus wave shape, because in a sinus wave shape we always are charging and discharging the cable. So we will have a combination of liquid current plus charging current. And for the reason is that one of the advantages and disadvantages of both wave shapes. Now, talking of the different parameters that we will measure with the tan delta test, the first one is, of course, the mean value of the tan delta. The mean value of the tan delta are all the individual values of the tan delta for each voltage step. We will add all the individual values of the tan delta test for each voltage step, and we will divide them by the total number of measurements. In this case, that number is 30. As you can see in this equation, we have the mean value of the tan delta is the summatory of all the individual values of the tan delta for each voltage step, and we will divide them by the number of measurements. In this case, is 30 because we have 10, 10, and 10. The second parameter we will measure is the delta of the tan delta. That is the mean value of the tan delta we get at 1.5 u-naught, and we will subtract the mean value of the tan delta at 0.5 u-naught. As you can see, the delta of the tan delta is the mean value of the tan delta at 1.5 u-naught minus the mean value of the tan delta at 0.5 u-naught. And the last parameter we will measure will be the stability of the tan delta of the standard deviation, which means how far or how close among them are the different individual values of the tan delta. For instance, for the first voltage step, 0.5, you can see that the individual values are very close each to other. In the second voltage step, they are very dispersed. You can see that the values are very dispersed, and it's pretty much the same for the last voltage step. The magnitude of this value is quite different of the last one. So that is the standard deviation, which means how is the behavior of the tan delta as we increase the voltage. So once we have done with the tan delta test, we can take the different condition assessment, the different parameters, and compare with the respective table in the IEEE 400.2. In this case, we are seeing the table 4 that is for PE XLP cables. And in this table, we have 3 different condition assessment: no action required, further study advisor, and action required, which means that, for instance, no action required means that no indication of severe problem in the short term. The cable system can be returned to service, and the cable system should be retested at some later date, maybe 4 years. No action required means that we have pretty much a cable with a good insulation, so we can repeat the tan delta test maybe in 4 years. If we have if the assessment criteria is further study advised, means that we need additional information to make an assessment. Maybe we need to compare the historical tan delta results of the tested cable and see the behavior of the different parameters through the time. We can do also additional diagnostics tests, for instance, monitored with stand test, or we can do a visual analysis, a visual inspection of my cable to see if we have, for instance, wet splices or wet terminations. If we have, the last one is the action required. If we have the assessment criteria is action required, means that we have a really poor insulation condition and the cable system should be considered for replacement or repair immediately. It's very important that we keep in mind that if we are doing by the first time a 10 delta test, we will not be able to make a decision regarding that cable. If we, for instance, if we do a 10 delta test and the assessment criteria I got is action required, that don't means that I need to change my cable immediately. What maybe I need to do is put back the cable in service and repeat the 10 delta test in 1 year and see the behavior of the tip up or the delta of the 10 delta and the standard deviation to see, to try to take a decision, but never took a decision or take a decision from one first measurement of the 10 delta. Talking of the voltage dependency of the 10 delta in P and XLP cables, we have this graph that shows very clear that, for instance, for a reference cable, a new cable, or a slightly service-aged cable, we have the red graph and the yellow one, and you can see that both graphs are pretty much flat lines. But if we see the strongly service-aged graph of a cable, that is the blue one, you can see how, as we increase the voltage, the dissipation factor increases. So, of course, we know that there is a voltage dependency of the 10 delta for PE and XLP cables. As we increase the voltage in very aged cables, we have an increase of the 10 delta. And is the same for the paper insulated cables. And you see this graph for a very poorly impregnated cable, as we increase the voltage, the loss factor increases, and for a well impregnated cable, that line is almost flat. So the voltage dependency exists for both type of insulations, polymeric insulations, and paper insulated cables. And to show you some results of the 10 delta, in this graph we are seeing 10 delta and good cables. You can see that the three phases have pretty much the same behavior. Of course, we have some little increase of the 10 delta as we increase the voltage, but this is a good result. In the next slide, we see how the weather conditions can affect the measurement of the 10 delta. In the graph in the left, we see that we did this 10 delta test during a rain. So you can see the values, for instance, for the phase L3 are high. We have a value of 7, almost 7. The maximum that we reached was a value of 7 for the 10 delta. In the same circuit, for a sunny day, we have a better results. You can see that for the same line, the same phase, the L3, we have and the maximum we reached was 5. The value was 5. So also the weather conditions could affect the results of the 10 delta. And the last one is we'll say a little strange behavior, because what is really strange is that we start the test and we have very high values of the 10 delta. But as we continue doing the test, we get a little, we improve the values of the 10 delta, and when we reach the 19 kV, there is some kind of stabilization of the 10 delta, and we start to have a normal behavior. What happened here is that we start with a lot of water in the cable, the cable was wet, and when we start the 10 delta test, we put some current in the cable, and that current evaporated the water. For the reason is we are getting a little better 10 delta in the first half of the test, and in the last half of the test is what we will say normal behavior for the 10 delta test. So what are the limitations of the 10 delta? Well, the frequency must be 0.1 hertz. If other frequency than 0.1 hertz is used, then we cannot use the tables of the IEEE 400.2 to evaluate the 10 delta, because they are linked to the frequency of 0.1 hertz. We have limited length in the cables. They're just around 3 kilometers. And in 3 retardant XLPE insulations, the 10 delta becomes less important due to the few wire trees existence in this kind of insulation. And of course, must be a single type of cable insulation. If we have a mixed cable, for instance, a paper insulated cable mixed with a XLP insulation, well, the different insulation will match the defects that we can have. So there is some of the limitation of the 10 delta. So doing a brief summary of the 10 delta test, the 10 delta test is an scalar quantity. It's a dimensionless unit. We measure the angle and the ratio of the resistive versus to the capacitive current. As cable age, the insulation resistance decreases, the resistive current increases, and the angle increases. And we will compare the angle of the 10 delta with the IEEE 400.2 2013. In order we will be able to make an assessment. Here we have some of the units that we have in Megger. Indeed, Megger is the only company that can provide both VLF with both kind of technologies, the cosinus rectangular units and the VLF sinus units. In the left, we're seeing the cosinus rectangular. We have seen the VLF 28. We have also the VLF CR 40 kV and the VLF CR 60 kV. And that means for test 15 and 25 and 15, 25 and 30 and 6 and 30 kV cables. And in the right, we're seeing the sinus units. We have the smallest unit we have is the VLF sinus 34. Then we have the VLF sinus 45, and the last one is the VLF sinus 62. And for finish this webinar, I will do a simulation of how we normally do a VLF test and a 10 delta test. I will use the VLF sinus 45 kV. The way we connect the unit is, as you see in the picture, first we connect the safety ground, then we connect the test lead of the cable. The first connection is to the concentric or the shield of my cable, metallic shield of my cable, and then I will connect to the center conductor of the cable inductors, and the last one is the power cord to supply voltage to my VLF. The control panel, in the control panel, we have, of course, the emergency off button, the on-off button, the high voltage interlock key. The high voltage on is the green button. The high voltage off is the red one. We have the USB port, the display, and this rotary knob or rotary encoder will help me to go through all the software in my VLF. So I'll try to replicate in this slide the buttons and the controls that I need to operate my VLF. The first that I need to do is to turn my rotary knob to select the test option. And now I will click on the test option, and I will have access to all the tests I can do with my VLF, which are the DC high pod, the VLF test, and the 10 delta. In this case, I will select the VLF, and I will click on it. And now I need to select in which phase I will do my VLF test. I will select the phase, I don't know, Alt2, and we'll click one more time. And now I need to select the VLF test voltage for my test. I can go up to 45 kV in this unit. So I will go to the maximum. I will click on it. And now I need to select the test time for my VLF test. So I can select 90 minutes or infinite. For instance, if I decrease the frequency and I need to do a VLF test during maybe 2 or 3 hours, I can leave the unit in infinite and the unit will work for 3 hours. But for this example, I will select 5 minutes. I click on it and I'm ready to start with my VLF test. The only that I need to do is to press one more time the rotary knob to start the test. The unit will ask me to push the high voltage on because the unit never ever will activate a high voltage for its own. So I press high voltage on, and the VLF test will start. Of course, I will have access to all the main parameters during the test, the insulation resistance measurement, the capacitance of the cable, the frequency, the peak voltage I am applying, and the time. I have also a countdown clock over here with the time, and in this case, I'm doing the VLF test in the phase 2. Once we're done with the test, the unit will discharge the cable and will display the message test successfully finished, which means that this cable holds the voltage during the 5 minutes. Okay, so we have a successfully a VLF test. Now, if I want to do a tan delta, the only that I need to do is to click on the back arrow. I will click, and I need to select the tan delta option. I click on tan delta. I select, in this case, I will select the phase L1. I need to select the standard under which I will run my tan delta test. I will click on IEEE 400.2. I need to select the insulation type. I will select P and PXLP insulation. And now I need to select the unit voltage for my tan delta test. I will select 10 kV, and I click one more time on 10 kV, and the unit will display the 3 voltage steps that will apply. The first one, the first level is 0.5 U0. Remember that U0 is 10 kV, so 0.5 U0 are 5 kV. 1 U0 is 10 kV, of course, and 1.5 U0 is 15 kV. So I click on OK, and I need to click start to start with the tan delta test. I click on start, and the unit allows me to connect the phase L1. I click on OK, and the unit one more time will ask me to push the high voltage on, to apply the high voltage. I click on high voltage, and the unit will start with the tan delta test. In this case, we are applying three voltage steps, and in each voltage, I will measure 5 times the values of the tan delta, and you can see that we have the 3 voltage steps. Here is the first one, 5 kV. Here we have 15 kV, and here we have, it's 5 kV, 10 kV, and 15 kV. And for each voltage step, we have the 5 tan delta values for each voltage step. Once we're done with the VLF test, with the tan delta test, the unit will say test successfully finished. I click on OK, and we will have access to all the important information, the mean value of the tan delta, the tan delta stability, and the delta of the tan delta, and we will have the assessment for the tan delta test. In this case, is action required. We can download the information from with the memory stick, or we can leave the measurement in the internal memory of the unit. We have a really big internal memory in the VLF units, up to 1,000 measurements, and so we can download whatever we want, the measurements we have done with the VLF, and we will have the report, a really nice report with all the graph of the tan delta measurements, and with all the important information, as could be the tan delta value, the delta of the tan delta, and the standard deviation. So we will have all the important information in the report. And this is the last slide for this presentation. If you want to look for more, if you need more information regarding VLF test, tan delta test, or partial discharge, please go to the web page of Megger. In the web page of Megger, we have the webinars, and you can go through all the webinars we have for cables infrastructure. Also, we have some videos of the last webinars in YouTube. So please visit us, and if you have questions right now, we are ready. Thanks, Michael.
All right, thanks a lot, Javier. So obviously at this point, the presentation portion of the webinar is officially concluded. We'll take some time to answer as many of your questions as possible. If you have any questions, please submit them now into the Q&A box on the right side of your screen. For those of you that are leaving, when you close the webinar window, a survey should pop up on the screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve upon future webinars. On the survey, there's a field where you can also request a demo or a quote of any Megger products. A copy of the presentation, certificate of attendance, and a link to the video recording of this webinar will be emailed to everybody in about 2 business days. You can also view video recordings of previous webinars on our website at us.megger.com/webinars and register for our next webinar this Friday, offline partial discharge testing of rotating machines. The presenter will be Charles Nybeck. All right, let's jump into the questions. Our first one I'm going to send over to Henning. Henning, besides the tan delta, what other tests are available to detect aging conditions? It looks like Henning might have lost connection. We're going to, while he fixes that, we're going to jump over to the second question to Robert. Robert, you with us?
I'm here.
All right, excellent. So, what are IEC standards for for the testing mentioned on slide 8?
The IEC standards, so this is how it works. IEC itself does not have a dedicated VLF standard. Okay, it has all kinds of like apparatus standards and test practices standards, and there's one for high voltage testing. And this standard, the 660, it contains also cables, cable testing, after laying installation, everything, and it will refer you to a regional standard, which in this case is Senelec. And Senelec has 2 parts that are relevant for this, HD 620 and 621. S1, that's the full length, and that contains the test parameters for VLF testing, okay? And in line with this is the German VDE, the 2076, which is the VLF standard for Germany, where all of this actually originates. And there is a second IEC standard, and that standard is specifically just about after laying test, okay? So it doesn't contain any test parameters or mentions anything else for serviced age cable or whatsoever. So there's one that contains 3 times U0, and under the condition that you do a more monitoring, not just the bare VLF test, you can cut down the testing time to 15 minutes. So 3 times operating voltage RMS, 15 minutes on new cables. That's the second alternative IEC standard.
All right, thank you, Robert. I'm going to jump in real quick with a question I can actually answer. The question being, how will I get the certificate of attendance for this webinar? The answer is we will send it to the email you used to register for this webinar. Now that we're with that, we have our first question back over to Henning. Besides the tan delta test, what other tests are available to detect aging conditions?
Well, probably today, the most utilized test to detect aging conditions is a tan delta test, because it measures the change in dielectric properties of an insulation material, which can be caused by water-free aging is one of them, but it could be also be thermal aging, for instance. It could be chemical aging. Whatever breaks up the molecular structure of the XLPE insulation and affects it will be measured by measuring the dielectric losses in the insulation. There has been used one other method to specifically determine the amount of water-free growing in cables, and that was the isolation relaxation current method, which was used in certain parts of the world very successfully, but never caught on over here in the North American market. But overall, 10 delta is the state-of-the-art method to really get the aging condition. In the old days, one would do a leakage current test, but that implies you use a DC test, which basically on all solid dielectric cables is not called for anymore. And also water trees, and that was one of the reasons why actually VLF testing was developed. One of the reasons is because water trees are not really detectable with leakage current unless you have a very large amount of water trees. You would also have an increase in leakage current. But the 10 delta is a much more sensitive method to detect it.
All right, thank you, Henning. Robert, what is the max and min band bending radius for a 15 kV, 25 kV, and 35 kV?
It's a very simple answer to give. That depends on the cable. So there is no general parameter for that. It depends on the construction of the cable, because there's all kinds of 15, 25, 35 kV cables. So just go with the manufacturer specifications. The data sheet always contains that. If you buy it from, I don't know, Nexans or Prismian or whatever, whoever you buy it from, they have a data sheet, and that contains all the information, ratings, and the bending radius, and just adhere to this and adhere to your working practices, and that's the answer to that.
Maybe there are two more comments on this. First of all, obviously it depends also on the diameter of the cable. Smaller diameter cable have smaller bending radii, and the other thing is, which is very different when you have solid core cable compared to stranded core cables. The solid core cable are much more sensitive to bending radius than when you have stranded conductors.
All right, thank you. Henning, while we have you, can we combine a VLF and tan delta test together?
Well, actually, that is part of the reissued 400.2, IEEE 400.2 from 2013, where there is talk about the or description about the monitor withstand test, and so basically that is really a combination of exactly those two tests. You basically perform a VLF withstand test, and while you're performing the withstand test, you also monitoring the 10 delta trend as a parameter. And it's a little bit like in the old days, the leakage current, when you measured the leakage current during the ongoing DC high-pot test, and you were looking for the leakage current to basically eventually to go down. With a VLF, with the 10 delta trending, you looking at the 10 delta staying flat and not having an increase. If you see an increase, that is a clear indication that something is happening while you do the withstand test in the cable, and normally that is nothing good. So that's the best. I think it's a good test. The monitor withstand test, I think, is something that should be explored overall much more. Just a brief comment on it. You can use either 10 delta. You can also use PD as an indicator, or you can also use leakage current if you use the cosine rectangular like Javier was talking about.
All right, thank you. Robert, what is the difference between EPR and XLPE?
Well, a chemical question. Well, okay, the principal difference is that XLPE is a pure insulation material, and EPR is a so-called filled insulation material. On a chemical level, EPR belongs to the class of so-called copolymer cable, and it's called copolymer because you use two, let's say, basic structures that you create the chains and then the cross-linking with. So you have ethene and propene. So this is why it's called ethylene propylene rubber. And XLP is just a cross-linked polyethylene. On an electrical level, XL or EPR is the inferior insulation material. This is why it's not used in high voltage cable, with some very specific, almost irrelevant exceptions. Anything that is 110 kV and above is XLPE. And this will never change because of the losses. It has a few other properties that make it somewhat attractive to certain areas of the world. So overall, you can say pretty much outside of, let's say, North America, very roughly, most people don't care for EPR. Let's say we are a manufacturer of equipment as well, so we like EPR as well for our test leads because it's flexible, and that is the property that some people like. It's easier to handle it mechanically, but from any other point of view, XLP is the way to go. It's also cheaper, and in the 10 delta standard here, or let's say guideline, you will have separate tables for the values for these so-called mineral cables or filled cables. And sometimes to illustrate the difference a bit more, to make it clear to somebody who has no interest in chemistry or whatever, you can compare these two things with coffee, okay? So the XLP is the very nice Colombian coffee, okay, the pinnacle of coffee, right? And the EPR is your hotel blend, right? It's a mixture of different types of coffees, and then there's filler material in there. So that's the main difference. So losses higher in EPR, mechanical flexibility higher in EPR. And one more word regarding 10 delta and VLF, both materials tree. So it's not that only XLPE is suffering water treeing, EPR has the same effect. And the latest generation tree retardant XLPE has about the same tree growth, behavior as EPR.
All right, thank you, Robert. Henning, what insulation resistance minimum and maximum values will be considered as good cables in medium voltage cables?
Well, when we talk about medium voltage cables, we have to differentiate between solid dielectric cables and there are still quite a number of paper insulated cables, which is, the PILC cables. So you can say the solid dielectric cables, obviously the insulation resistance of a good cable should be in excess of 100 megohms at least. Typically, you are in the giga or tera ohms on a good cable, and the PLC cables are a little lower. Typically, a good paper cable might be in the range of let's say maybe 50 megohms. So it is a little lower, but the solid dielectric cables are really very, very high in the insulation resistance. And a maximum, there is no maximum. The higher the better. Okay, so it's only the minimum that you get concerned about, because the minimum indicates there are problems in the insulation.
All right, thank you, Henning. Robert, do you know when the VLF test standards will be updated to include high voltage EPR cables?
So I cannot speak for IEEE, But overall, IEC and SIGRE are working on recommendations and those recommendations will lead up to a standard sooner or later regarding high voltage cables. However, right now, this is not done. It's at the horizon, it's coming up, but it has not yet happened. IEEE, I'm not sure, they already include 69 kV cables, which is, a little bit odd because like IEC took or drew the line at 36 kV rated cables, and which also causes a little bit of confusion in the field then, because we see an increasing number on 66 kV cables and so forth, and people are asking for VLF. So in that case, you don't really have a standard yet in the IEC world, but there's workarounds. But I cannot give you a date when this the new standard for high voltage cables will be ready.
All right, thank you, Robert. Additionally, what is the highest voltage for current VLF instruments?
So that depends on the wave shape as Javier described. So the sinusoidal units, they go higher up in terms of peak voltage, because that's the requirement mainly of IEEE 400.2. So if you look up in the table for the 69 kV cables, you'll find 119 peak. The highest commercially available, like regular medium voltage cosine units, they max out at 80 kV RMS, which is the equivalent to the 119 peak as Javier described. So with the CR80, that's the same as testing with 119 kV sinusoidal unit.
All right, thank you, Robert. Henning, how long is the dampened AC ramp charging time as compared to PF, CR, and sine?
Okay, that's an interesting question, which was talked about a lot during the development of the IEEE 400.4. Obviously, let me start with the power frequency. Obviously, its power frequency is whatever power frequency, 60 hertz. What is it? 8 milliseconds. That's what you have available for charging the cable. In the CR, you have depends a little bit the frequency of the during the transition from negative to positive polarity depends a little bit on the cable capacitance, how big that is, but typically between, let's say, 5 and 15 milliseconds. So it is basically very clearly in the same range as power frequency is. Sinusoidal, we know we have 5 seconds to charge, so you can say roughly 1,000 times more time to charge the cable. And the damped AC is depending purely on the cable capacitance and on the current that the unit can supply. For medium voltage cable, it's typically a few seconds. For really, let's say, high voltage cables, let's say if you go to maybe 138 kV or 230 kV, it could be a little bit longer, but still it is basically always in a time range that is not coming close nowhere to the problem of creating space charges in the cable, because you're using a DC voltage to charge the cable up to that voltage before you get the damped AC wave shape. So the DAC is probably the longest one from all these when you compare them. And the shortest is power frequency, and everything else is in between.
All right, thank you, Henning. Robert, could you please shed some light on VLF testing on medium voltage IEC manufactured cables and the applicable voltages for VLF testing?
Okay, lots of IC questions here. Okay, so the way this all originated was VLF came up in the 1980s because then these issues with the DC testing on the solid dielectric cables came up. A certain company patented this technology, and it got widespread into the industry, and it was pretty much became a quasi standard, and then it became a standard. So that standard migrated through the levels and is now pretty much the standard waveform for all of this. And then in the 90s also simultaneously the sinusoidal technology evolved. So from the beginning, this 3 times operating voltage, 3U naught, is the typical IEC testing parameter. So if you test cables in the IEC world, for new cables, the so-called after laying test or after installation test, which is, in American English, the commissioning test, is 3 times operating voltage. And 60 minutes is typically the recommended time. Now, keep that in mind, recently, that's a trend. Because of what utilities see and manufacturers see and all of this time for the after laying test has been reduced with one condition: if you do a monitored withstand. And here we're not talking about monitored withstand with 10 delta, because that's a useless test on new cables. We're talking PD. So if you talk to, let's say, Europeans, Middle Eastern, all of these areas, the monitored withstand is the VLF test. You have to do it. It's the over voltage test. And plus monitoring the PD during commissioning. So that is very common, and it's now the latest, hottest trend. And the standards, the committees are now getting slowly in motion. It's like, they need a little bit of time to gain inertia. You know how this is. And now it starts to become evident that more and more amendments at first are made before the big revisions of the standards are being published to allow for this monitored withstand. So VLF at 3U0 or some other test value at reduced testing time if you do PD. So just to give you one example that is very common, let's say in the IEC world, for instance, in Central Europe, what they would do is they test at 3U0, and if they have, if the cable has a history, okay, of failures, let's say if it's a serviced age cables, and you had more than 2 failures already on the circuit, that's a rule of thumb again. This is what the utilities do very often. You have more than 2 failures, they would reduce the test value, but not the time. That stays at 60 minutes. But they reduce the voltage, for instance, from 3U0 to 2U0, just as an example. And if you then have, for a serviced age cable, a failure, they would reduce it even more, but never below 1.7U0, and they would apply it for, let's say, 5 minutes. And this is a kind of a Hail Mary, okay? So everything failed. So they started with the normal test. They knew it was a troubled cable. They reduced it to 2U0. It failed during the 60 minutes. Now they do 1.7 for 5 minutes, and hopefully it passes. And now understand this. This is not really a proper withstand test anymore. This is just, oh, we have a really, troubled cable, a bad cable. They just do some test to be sure when they re-energize the cable's okay, and they would immediately schedule that cable for replacement, because 1.7, you know where this number comes from, is the over voltage factor for the ground fault. Okay, so they just want to make sure, okay, if I turn back on, the voltage on the circuit, it's not just gonna, blow the fuse again and trip. So that's a typical procedure. But the standard itself, IEC, after laying test, 3 times operating voltage, and also very important, one last thing. So 3 or not 60 minutes, very typically 30 to 60 minutes on new cables, and strictly at 0.1 hertz. So IEC does not really allow for frequency reduction. That's a let's say a little bit of an let's say it's a loophole in IEEE. So that allows to accommodate the low power sinusoidal units to go on much longer circuits where, IEC simply does not recognize that.
All right, thank you, Robert. Henning, during tan delta tests of cables, the voltage levels are 0.5 U-naught, 1 U-naught, and 1.5 U-naught are applicable for 15 kV, 25 kV, and 35 kV cable testing. Could you comment on that?
Well, tan delta is, like we said before, measuring dielectric losses. And to see what the losses are, we put an electrical stress on the cable by applying a voltage. Since these cables, these medium voltage cables that you mentioned here, and all medium voltage cables, they are designed for a certain stress in the insulation. And since that stress level is the same, whether it's a 15, almost the same, 15, 25, or 35 kV cable, that means we can also use the same stress level when we do tan delta testing. That's why the numbers are the same, whether you have 15, 25, or 35 kV cable.
Hey, Henning. So, Robert, are there recognized standards for the tan delta test value?
For the tender, well, as Javier presented, there is the tables in IEEE 400.2. So for comparison and for the assessment in these 3 categories, no action required, further study advised, and action required, by the 3 mean tan delta, stability, and tip up. In IEC, just to capture that question as well, there is no such thing. There is a testing practice in the real world, but that is not anywhere to be found in a formalized IEC guideline or standard. So the typical what's called quote unquote European test practice, they go up to 2 times operating voltage, not just 1.5. And there's also some other differences, so to speak. So pretty much when you talk tan delta and you really want a guideline, go with IEEE 400.2.
All right, thank you, Robert. I want to squeeze in one last question today, and while I have you, I'm going to send it over to you. For tan delta testing, based upon the difference between 1.5 U-naught and 0.5 U-naught, what can it tell us about the condition of the cable based upon the IEEE and IEC standards?
Is that for me or for Henning?
Sorry, that'll be for you, Robert.
Okay, so did I get this right? The tip up, what can it tell us about the condition? Well, the tip up is typically sensitive to the water content in the cable. So you see all kinds of like weird things when there's local water, and for instance, we had examples sent to us where one of the joints in a customer's cable circuit was completely filled with water, and they had a negative tip up. So the value at 0.5 was the highest, then at 1 U-naught was kind of in between, and the lowest was at 1.5. Another thing that you see very often if you have water in the cable is that you have a tip up from 0.5 to 1, and then you have a flat curve, so to speak, from 1 U-naught, 1 operating voltage, to 1.5 times operating voltage, which is, typically also expected to go up as well and not like flat like that. So the tip up is typically a very good indication that you have water in the cable.
Maybe one
All right,
other
thank you.
comment on that. If you had a tip up, let's say you have a fairly gradual increase between 0.5 and 1, but when you go to 1.5, you have a very substantial tip up. And that could sometimes mean you have partial discharge in the cable happening at that voltage, okay? Because obviously, once you have a discharge, that means the dielectric losses go up like crazy. So sometimes it's it's very important to really watch not only the negative tip up but also the positive tip up, because it can be also very clear indication of some severe damage into the cable.
All right, thank you both. That was a great answer for our last question of the day, because it does look like that's all the time we have for our Q&A session. We apologize if we did not get to your question today, but we will follow up with you offline in the following weeks. But I'd like to thank you all for attending. If you could, please remember to answer our survey. That survey will include a field for you to request a quote or a demo if you're interested. But once again, I'd like to thank you all for attending, and I hope you all have a great week.